Okay, so good morning and good evening, everyone. For those who join from US, welcome to the EvoAgentX Talk. So I'm CV, the co-founder of the EvoAgentX team, and thank you all for being here. So for those new to this series, EvoAgentX Talk is where we bring researchers working at the frontier of foundation agents to share the ideas shaping how agents learn, reason, and improve. And today's topic sits right at the frontier. So most agents we build today are, in a sense, frozen the moment we deploy them, fixed prompts, static tools, predefined workflows. So here is the question. We are really asking today, can an agent keep getting better while it's actually running? So to dig into that, we are honored to welcome Seth. Seth is a PhD candidate in computer science at Princeton University and a researcher at Prime Intellect, where he works on agents data evaluations. Before Princeton, he earned his MS in robotics at CMU. His research focused on foundation agents, multi-agent system, generalized harness for embodied agents, and alignments and safety. And his work has been supported by the NSF Graduate Research Fellowship and Google DeepMind Research Grant. So today he will be speaking on Continual Harness, online adaptation for self-improving foundation agents with some fun demos along the way, from Gemini plays Pokemon Go to self-improving coding agents. With that sense, the floor is yours. We are really excited to have you here.
Great. Thank you so much for having me, everyone. I do like to try to make these talks a little interactive. So perhaps after a couple slides, I'll check the chat. And if there's any questions, I can address them. And then I can take the majority of questions at the end. Let me share my screen. All right. Can I get a quick thumbs up if you can see this all right?
Yes, we can see the screen.
Great. Thank you so much. Okay, so thanks for the great introduction. I'm very happy to be here presenting my work on Continual Harness online adaptation for self-improving foundation agents. This was work that was completed while I was at Princeton for my PhD. And I think I do see one of our co-authors in the attendance today. So I could not have done this without my amazing co-authors as well. So in this talk, I'm going to go over three things. The main item that I'm going to go over is looking at the Continual Harness paper with the Gemini Plays Pokemon results. Afterwards, we're going to look at some extensions on Arc AGI 3. And I have a very nice treat for everyone. The Continual Harness paper has been turned into a commands line interface agent, coding agent, called Prime Agent. From my Prime Intellect work. So I'll go over some quick results for a continual harness agent that you can download today. So there are a lot of different coding agents out there, from Claude Code, OpenHands, and Cursor. Each of these agents have a variety of different features, and a lot of them are set up with a particular model. They have a set of tools in their coding harness in order to help alleviate issues when interacting with the software world. You can typically see compaction being used by all of our agents now, which is kind of like a sub-agent that directly, or a tool that directly summarizes the context history so that we can have longer running sessions. Or you might see a lot of more modern agents like Hermes agents, which have other tools and memories so they can learn over time. These setups are engineered to edit mainly between runs. And in this paper, we go over a reset-free domain, which means that we can leverage experience online in order to update the harness itself. Additionally, we look at domains that are not just coding, but we look at these embodied and long horizon domains in games. In those settings, in addition to having your context history, we'll have state information such as a frame of a video game Pokemon, the map that the characters can walk around on, as well as a button interface for playing the game. From there, this is the basic information that we give it, and then it is up to the harness of the agent in order to leverage its experience in order to make memories and progress along this game. So to begin with, we're going to focus on LLMs that have played these Pokemon games. As I previously mentioned, it has the rendered frame as well as the ASCII map in order to see what's going on inside the game, and it has a set of very normal buttons if you've ever played Game Boy or Game Boy Advance. You have your up, down, left, right, A, B, start, and select buttons. We don't give it any special settings there. In each of the games, we look at a subset of the milestones that you can progress through. In Pokemon Red, we're going to look through the 18 milestones, and Pokemon Emerald, we're going to look through 31. If you have been following a lot of the LLMs playing Pokemon, you will have seen one of our co-authors, very, very famous, very public work called Gemini Plays Pokemon. And most of the harness design here was using human-in-the-loop harness development. The agent plays the game, creates observations and acts in the environment, and will then create some trajectory. A human looks at this trajectory and then updates the harness, updating the prompt guidance, giving it special tools such as pathfinding, and then playing the game, letting it play the game again. This is the first instance of a human-in-the-loop refiner, and it did very, very well. In May 2025, the Gemini Plays Pokemon agent completed the entirety of Pokemon Blue, being the first agent to complete the first LLM agent to complete a full Pokemon game. In August of 2025, we went to a much more rigorous domain where they completed the Pokemon Yellow Legacy elite mode on hard mode. So there were a special set of rules that were added in order to make the game harder. And then famously, it also completed Pokemon Crystal without losing a single battle in November of 2025. So we can already see some improvements that are both a result of the model and the harness and the human refiner going throughout this and getting amazing results. But we still need to quantify how good these things are from an evaluated point of view. So with respect to the harness, if you're thinking about what type of skills are necessary to play a Pokemon game over the entirety of it, luckily for you, we have hundreds of thousands of turns from Gemini Plays Pokemon where we know exactly what skills were created by the agent and then what it was using them for. And you can see that it starts out with a lot of sub-agents in order to do specific functions, and then it builds these reusable skills throughout the games and calls them quite often. You can see also that the skill usage is not static. Different skills are necessary through different parts of the game. For instance, you'll always need to have some sort of pathfinding skill. You can think of this as a Dijkstra or an A-star algorithm where it can efficiently traverse to a certain location in the game. There are also battle strategist agents. These agents are used to do the Pokemon battles within the game. So you can think of that as the zero-sum strategy solvers, as well as specific puzzle solvers. So if you've played Pokemon before, you know there are puzzles such as you have to move a set of boulders around in order to progress through an area. And so it created specific skills just to address these complex problems along the way and then updates and refines them. What's very interesting is that if you look at the reasoning pattern throughout this, you can also see the total depth and breadth of the reasoning change with respect. So we're seeing live harness refinement that reflects the change in the thinking pattern of the agent throughout the game. And what happens is that when you're going throughout these games, we can get stopped for days at a time sometimes in Gemini Plays Pokemon. There's no explicit feedback necessarily that shows that the agent is stuck. And for instance, there are some, if you watched any of the live streams, you can see that the agent was doing the same repetitive thing over and over and over again. And sometimes it would get stuck in a loop until what happened to be a random chance to get it out of it. This was a very large motivating experiment between the types of skills and thinking that we saw in Gemini Plays Pokemon in order to formalize this into an abstraction. And we decided that this abstraction is going to live over these 4 components that are very generalizable. You can think of it as the prompt or the system prompt. And this has specific guidance and information in the history that you want to persist across compactions. There are subagents. These are delegated specialists that have a specific prompt and history so that the, let's say that we keep running into wild Pokemon battles, the subagents can handle the battle so that we don't lose useful history of the overall plan of how we're progressing throughout the game. So that way we can make sure that our context is managed better. There are also skills. The biggest use of skills was using breadth first search or other pathfinding algorithms in order to traverse through the game, because a lot of the game requires traversal. And then finally, memories. What have we achieved so far? Did we defeat the gym leader? Did we catch a certain Pokemon? All of this is important to keep in context, and being able to legibly write down memories is very important so that they can persist across compactions. Now, the way we have structured Continual Harness is to leverage this set of abstractions that were based on Gemini Plays Pokemon. And then we also wanted to take the fact that we know that the agent can do some updates, but isn't the best at necessarily applying them and leveraging the experience. So when we think about how we want to do refinement, we want to collect these trajectories of these actions and then leverage this experience as a set of these trajectories that can be read. You can think of it as some last F steps that we're reading through. And then finally, based on this experience, we can have you can think of this as a subagent or a skill, but basically it's a separate prompt for an instance of the agent that is specifically reflecting on the past experience and then making a set of edits to the prompts, subagent skills, and memories in the harness set of files, and can immediately edit these before we continue playing the game further. This allows us to make sure that we're properly leveraging our current experience in order to be forward-looking and not repeat the same thinking that was required previously. So for instance, for all of these edits, we make this as generalizable as possible. I say that abstractions matter a lot when you think about this thing. So what kind of operations can you edit to each of the prompts, subagents, skills, and memories? Well, we call these CRUD operations, which from computer systems. It's just creating new ones, reading existing ones, updating existing ones, and deleting old ones. We find that there is a set of like context rot that you can think of with these skills, where it will add lots of you can see all these skills that were created, and it'll create and add lots of these different skills that are repetitive and overused for the same exact thing. What we want to do is have one pathfinding skill that we constantly update over time so that we perfect it towards, you can imagine it might start out as something like breadth first search, and then it builds into, realizes it can build it into like a Dijkstra's type of search. And then finally, you can use A*, right? You can apply heuristics. This is a very natural paradigm in order to update over time. And that's the type of behavior that we'd want to see. So we want to leverage the set of abstractions such that it is easy to process the information over this to say, okay, from this trajectory with this skill, I see this performance, right? You have the information, the experience. You have the goal, right? We're trying to make a very efficient pathfinding algorithm. And then you can see the actual execution. How did it get stuck? Was it able to successfully navigate where it wanted to? And so what Refine's doing is kind of like editing over this state in order to make sure that we can increase the quality of our skills, make sure that those subagents creating are useful over time. And same thing for memories or their specific guidance. We compare with just naive reset-based prompt optimization that would complete between episodes. So we do it within a single episode, which means that we can leverage some trajectory window. We don't have to like restart the game from scratch, which is really useful in these very long context, long horizon evaluations where the actual runs that we did took days. And you don't want to restart from scratch when it takes days in order to complete a run. Okay, jumping to some of the results. So we have some really cool results in Pokemon Red and Pokemon Emerald. We also live streamed these results when they did come out live on YouTube so that people could check it out and experience the runs live. I think this is really important to really show the trust for your research and show that like you can see the agents figuring it out and updating in real time and read through the logs to understand what is going wrong and how to improve the harness's harness, right? The meta harness there. So we track in terms of cumulative button presses, how well each of the harness settings are doing. So let me go through them. We wanted to have some baseline harness. So that's as if you took some sort of coding agent and then you just said, go play Pokemon Red. Here's the state. Here's a way to grab the state, and here's a way to like perform actions in the game, pressing buttons. We call this HMIN. And you can see that in Pokemon Emerald, this received around 18,000 button operations in order to complete the third gym badge, the Thunder badge. And in Pokemon Emerald, it took 7,500 operations in order to get the second gym badge, the Knuckle badge. You can also see that these are kind of the lower bound for each of these runs, where if you don't have any expert or anything updated, it is worse. Now, before I get into the Continual Harness, the CH ones, we have 3 settings. I just want to talk about H Expert. So H Expert, we kind of think of as a human level ceiling. So if we could approach this level of performance, we are just as good as the Gemini Plays Pokemon developer who's sitting down, watching the trajectory runs, and then taking particular edits directly to the harness themselves. And as we've seen, they were fantastic at this. They were able to show their agent complete multiple Pokemon games as a result. But our question as a research problem is, how do we do this automatically, right? How do we get the harness in order to make those edits and leverage the experience so we can sit back and just watch it do it, the whole thing? And so now we have these 3 different settings. We call a Continual Harness from scratch. So from scratch means we start with HMIN, and then over time, we update the harness. So you can expect in the first couple 100 steps, there's no differences between HMIN and Continual Harness. But as you leverage more experience, you can continue to progress and increase. We found that this was able to improve by around 3,000 for Continual Harness over HMIN in Pokemon Red, and by around 2,000 steps to get to the second gym in Pokemon Emerald. What's interesting is that we wanted to see if there was strong value to using the Continual Harness and understand if it's actually making useful goals as it's going along or useful harness updates. And so we took 2 different settings of reusing the harness from the beginning of the game afterwards, just to check to see if this is actually helpful. And we found some very interesting results. We call these Bootstrap Frozen and Bootstrap Updated. So that means that we start from the finalized harness from the Continual Harness from scratch run, so after completing all the gym badges, and then we say, okay, go back to the beginning of the game using that harness. Let's see how much better it does. Let's see if it's able to approach the H Expert. And we find some mixed results. When the harness is frozen, we in both of the cases, we tend to get better results than from scratch because we already have the started harness. But the results may vary, one due to very long horizon variance, but also due to the fact that if we freeze the harness afterwards, it may almost like catastrophically forget how to use the harness if it's not updating. And so the performance is actually worse than allowing it to continue to update after this reset. It's only marginally worse, and it's about mixed results if you look at the Pokemon Emerald games. But we think it's important to consider that even if we're looking at a reset-free case, how does it compare to a baseline like human expert at creating a harness if we were to put it from scratch? There is still, I think the agents are very good at this and they're improving, but there's still a lot of work in order to progress past a human expert with this type of refinement. Yeah, I just went through all of these. Sorry, I had another slide for it. Right. So on top of that, we kind of wanted to understand what is the Pareto frontier of all of these different harnesses with respect to different models. Does this help frontier models? Does it help flash models? What about a light model? And so we did this across the Gemini 3 family. We had some nice sponsorship from Google DeepMind, which was kind enough in order to sponsor our runs. And so we evaluated strictly with Gemini here. I would imagine a similar case if you were on to use your favorite LLM that has a vision component as well from OpenAI, GPT, Claude, Kimi, whatever you like to use. And what's interesting is we discovered this almost Pareto frontier of these different cost versus performance portfolios with respect to a fixed 24-hour budget. So here we only give it 24 hours. How far can you get? How much money does it cost? And we found, to probably no one's surprise, that the pro models were able to do the best in terms of performance, followed by the flash models, followed by the light models. What's key that's interesting here is that if you look at the spend category, when you get to the pro level, the Continual Harness version that is updating is cheaper in the total run or to solve the task. But if you look at the flash level, the runs are not as cheap when it comes down to the HMIN versus Continual Harness. But we are able to see, despite some variance, we are able to see stronger performance overall. As you can see, that these were closer to approaching the 100% point than the HMIN runs. The flashlight models we found were not very useful at leveraging the harness. So we suspect that the smaller models, which are not as capable, are worse at leveraging these very state-of-the-art harness capabilities because they don't have the reasoning skills for that. So there's still a lot of room for improvement at the light or even the open source models for improvement. I think it's very interesting to think about from there. And so we wanted to even go further. One thing we have here, these are all frontier models that have a API cost associated with them. These are not open source models. So we wanted to see what could we do with like a 30 billion parameter model. Let me get back to that. So in quite 1 second, you're going to talk about around the 30 billion parameter model and see how well they do and how we can improve that through some training. But first, let's think about, I talked about actually measuring the quantitative aspects of the harness. Previously, we can say like, okay, continual harness, self-improving harness does better. But what is it actually doing better at, and by how much? What quantity can we measure this by to show that like this is actually a measurable improvement? And so one thing that we want to look at is this skill library. Are the skills that we're creating actually useful? I talked about these different harness components, and I think that we should be moving towards how to evaluate these harness components directly in order to see if this is a useful component. And is it a useful component on its own? And then two, is it being leveraged properly during the run? So on the left, what we did is we took the pathfinding skill that was being used throughout the run, and then we put it on a sample navigation task when compared to a Dijkstra oracle. And what's very interesting here is we have a very clear quantitative comparison approach between what the current pathfinding skill is and how how the true pathfinding algorithm would perform on a held out example. And we found to begin with, there's very strong increase in performance where the pathfinding skill goes from not having a pathfinding skill to approaching near the Dijkstra quality. But then after that, we kind of see almost like a skill rot over time where the model is not able, the model almost forgets and is actually decreasing in the skill quality over time, probably because it's reusing it or finds scenarios where it's not as, or where it was out of bounds on the data distribution on the edge cases. And I think this comes directly down to the fact that the navigation skill calls, when it first creates them, it's using lots and lots of skill calls. But then over time, you can see this logarithmic action to it, where the agent is not taking as many skill call actions over time. So there's still a large improvement that can be made by making sure that, one, you create skills that are useful and make sure they stay useful. And then two, once they stay useful, the model should be leveraging them rather than trying to do, let's say, manual navigation. As we said, most of these skills are actually never used again. So part of the continual harness abstraction is deleting and updating. And so rather than just creating 10, 20 of the same pathfinding skill or different variants of it, we should have one pathfind. The way we think about how models should behave is you should have one pathfinding skill, and the skill should be updated over time so that it is improving itself. For instance, in Pokemon Red, in our phase 2 runs, they created 335 skills. The number of skills that were invoked greater than once was 53 times, and greater than 3 times, 31, and then succeeded greater than 1 time is 14. So most of these skills, the model is actually terrible at using. So we're doing all of this hardness improvement, but the agent isn't successfully leveraging it. So there's huge opportunities in making sure that, one, we create useful skills, and then also make sure the model actually uses them. It's not good enough to create these nice abstractions. You need to make sure that your models are trained in a way such that it can leverage them efficiently. In addition to this, we have a different set of subagents that we used, right? So we wanted to take a look at skills. Now let's take a look at subagents. These subagents were used for a variety of different capabilities. What's really nice about this is that it actually is a lot cheaper for context tokens. So you save a lot of tokens because you don't have your full context in the window. You're just using a specific agent with a short prompt to battle or level up your Pokemon, grinding, or navigate, deal with dialogue or menus, or catching Pokemon. And this made it a lot cheaper to run the model. We found 8 to 11 times cheaper to use subagents versus an orchestrator. Since everyone wants to save token costs, I think that is a very easy argument for leveraging subagents. And then finally, the last item was the memories that we talked about. The memories that we're writing down, are they actually useful? Are they helping the model when you go forward, or are they written and then never read again? And so we actually look at, if you're writing the memories, are you actually using them? And for the most part, they are, except for a lot of the runs where it was writing 72 memories and then not really running them. We took a look at memories in one of the hardest regions of both of the games, the Mauville Gym in Pokemon Emerald and Mount Moon in Pokemon Red. These are two different segments of the game that were particularly difficult and take a long time because they require smart navigation as well as long-term thinking. So my takeaway is, as is with a lot of these other harness components, they're useful when used properly, but the models still need to be improved in order to leverage the harness fully. Okay, now jumping back, I said that we wanted to take a look at some open source models. So we ran Gemma 4 on Pokemon Red. And if you've ever tried this, unfortunately, that this does not work very well. They will make no progress. You'll waste hours of your day watching them run in circles at the beginning location. So we said, how do we make this advance? A big topic when we were thinking that was getting a lot of traction at the time was on-policy self-distillation. And so we said, okay, how can we leverage some experience from some of these smarter models in order to improve some of these weaker models? And you can imagine that if you had an intelligent enough model, it could potentially even improve itself. This is not really the main part of the paper, but I thought it's an interesting anecdote that we should chat about. And the idea is that, can we continue to make progress if we have a teacher that's able to basically relabel the experience the same way as Continual Harness is refining and looking at the trajectories? Given the experience, can it leverage this in order to provide some reward or some update about what it should have done, thinking in counterfactuals? And I have two things to say about it. One, it did work. So we did continue to see a progression in milestones where it was able to first it was able to achieve these different milestones from different starting points in the game with very few training iterations, very little amount of data. But there's two things about that. One, I think that there was a lot of overfitting that was going on, where the model isn't necessarily generalizing, it's just able to solve this new portion of the game. And the second thing is, you can imagine this is actually a batch size of one training run. And a batch size of one training run is very, very slow to collect all the experience and iterations that you need. So I think that it's interesting to show that you are able to do it. But I would also say this is not the bitter lesson way of thinking about this problem. I think for open source models, you need to leverage a lot more similar training data to the evaluation environment before you can then leverage a harness in order to improve in it. That is that the environments that work best with a harness are environments where there is an overlap in data with the training data. Great. So now we're going to move on to ArcAGI 3. So this was led by Rui, who is one of the co-authors on Continual Harness. And there's a couple, I think we're missing an author here potentially, but you can go check out the results also on continual-harness.github.io, where we have all of our results and you can see all the visualizations of the games. The idea here is we wanted to show that Continual Harness was not just a harness for Pokemon, but this is actually a general harness that can extrapolate to other potential environments. If you know anything about ArcAGI 3, it's a very difficult environment, especially when this paper came out. At the time, the best frontier model was Claude Opus 4.8, which received 1.5% on high mode. And then even when using the OpenClaw harness, it only received 5.2% using Claude Opus 4.7. And so these are very low scores for these environments. There's 25 public games that they need to solve. Each of the games has a hidden set of rules, mechanics, and scoring. There's no task description, there's no domain tools, and there's no legend for like what is going on in the game. They just received a kind of ASCII observation like this in the bottom left. And so this is very difficult and very challenging for symbolic manipulation skills of agents, and is considered one of the grand challenges every year. ArcAGI releases a new evaluation, and there's tons of people that care about this in order to show that their model is best. We argue that it's not just the model that matters, but also the harness can really effectively bring out the performance of the intrinsic capabilities of the models. So we ran our continual harness with Gemini 3 Pro, and this was able to achieve 20.5% on the public tasks at $774, which is no small feat, especially compared to the closed source model performance of Gemini, which is near 1%. It's not very good. When compared to a couple of the other open source harnesses that were out at the time, I know that the graph looks very different now. When it was at the time, there was like Alpha Evolved. There were people used like the Hermes agent that's very popular from the news, and then also OpenClaw. And these were all outperformed with this very general harness that was not developed specifically for our AGI 3. When we look at the results, we compared across like Continual Harness and Hermes because we thought Hermes was a very similar type of work as a general coding agent. What's very interesting is, like I said, there's no domain tools, and we have to learn what the rules are, which is exactly how Continual Harness works. It's taking the trajectory information and trying to make sense of it. It's trying to figure out what worked and what didn't work and why. And so this is very natural in this like refinement paradigm where you want to leverage the experience. ArcAGI, without trying to, became the evaluative suite to see how good your harness is at like self-improving. Because at the beginning, Continual Harness is just a normal harness for your agent. It's minimal. And then by the end of Continual Harness running ArcAGI, it's actually an ArcAGI harness because it developed all of those skills directly to play ArcAGI 3. We also found our performance when compared to from Continual Harness to Hermes, we found a lot more efficient skill and memory edits compared to Hermes agent, which mainly was running execute code throughout the tasks. When compared to Hermes agent, our model was a lot cheaper on the same levels. So each of these, like LP85, that is one of the 25 RKGI3 levels. Higher is better, so the higher final score is better, so to the right is better. And we found that Continual Harness basically completely outperforms across each of these levels. This is a sample of the top 6 games where we performed the best here. And we even solved one game 100% LP85, which is great. So excuse some of the Claudisms here. But one of the things that we did find with respect to the skills, when we did analyze this to see what's going on, what's actually useful in the Hermes agent. What's useful compared to Hermes agent that Continual Harness was able to do. And so we evaluated very qualitatively here to see what it's doing with the memory entries, what it's doing with the state changes, and then what different types of which actual skills and memories are actually being written down. After each of the levels, we ran the refine command. So if there was a game over, it immediately looked at the entire trajectory in order to see what went well and what did not go well. So it could update these different skills and memories along the way. And this was very useful to leverage the experience in order to directly get better at the game. I don't have much else to say about this. There's a lot of really cool demos on the continual-harness.github.io site that I definitely recommend that you check out. For the sake of time, I'm going to move on to the last item that I want to talk about, which is Prime Agent, which just came out today. This is something that I've led in some of my work at Prime Intellect. You can check out our blog post at primeintellect.aa/blog/prime-agent. You can also download this directly to use as your coding agent. Prime Agent is built upon a combination of the Continual Harness paper that I just mentioned, as well as the recursive language models paper from Alex Zhang, a co-author. If you don't know what a recursive language model is, it allows you to leverage coding abstractions within the harness. So then rather than having a set of files where you have a set of files for memories and skills and subagents and your prompt, you can imagine that if you just use a Python shell, like IPython REPL, you can take each of these components and put them directly in the REPL. And then it can just, since agents are the best at coding, it can directly manipulate each of these components in code, which allows it to be a lot more efficient with tokens and, I argue, be very good at symbolic reasoning. And so the combination of these two makes it they combine so nicely and they work very well together. So like I said, the only tool in this setup, rather than having like a skill and then like a memory and then like all of your MCP integrations, the only tool that we use is a Python REPL, a Python kernel where we have programmatic tool calling. This tool calling can directly create subagents, right? Like create a subagent to fix the failing test. It can update the harness from this. It can test and look for answers, and it can do that all asynchronously using the async IO package in Python. The most amazing part about this is that our best run with Prime Agent on ArcAGI3 using Opus 5 achieved 95.5% performance, essentially solving it. We ran 3 runs, one of them at 95, received 95% performance, another 95.2, and then our best one, 95.5. The best at 1 is fantastic. The best at 3, where we take the best combination of all of the runs, received 99.97 as its final score, completing all 183 out of 183 levels. This is strictly with Opus 5 that we found this performance. Previously in Continual Harness, we were only looking at Gemini 3. This is fantastic performance, and it really speaks to the power of the abstractions that we talked about, combined with the coding ability of these agents. And so when you define your abstractions as code, it's able to efficiently leverage and then reflect using the refine on your experience over time. In addition to ArcAGI3, we evaluated across a bunch of long horizon coding tasks. And you can find across many of these tasks that we compare PrimeAgent PA to PyMono. PrimeAgent is originally built on Pi, Claude Code, as well as Codex. And we found it's roughly the same or better than performance across all of these tasks. So PrimeAgent is not just a continual harness coding agent that is very useful for playing Pokemon or ArcAGI3. This is something you can use every day in order to improve your tasks, improve your day-to-day performance. Despite that, we still evaluated in some more games. So we tested it out in Factorio, which is a very popular factory building game. We set it up so it could use 4 different sub-agents in order to play, and leverage a MCP backend so it can use Archon controls in order to take actions in the game with 4 sub-agents that we get 4 players in the game. We apply the same thing. The refining and the memories still are able to abstract to another game environment that is kind of like building like a science factory where you need to progress through a tech tree. And we found a production score of hundreds of thousands, much higher than any previously reported scores in Factorio, just within hours. Unfortunately, in addition to 100,000 score, at the very end, we did find, and so a lot of issues right now is that models are getting very good, but they're getting even better at cheating. And so you have to be very careful when you look at your results of your evaluations and go through your trajectories in order to make sure that the model's traces do not display any signs of cheating. We give explicit instructions not to cheat, as well as we have an agent that monitors for cheating over time in order to avoid this. After a couple hours of the run, we found almost every time that the agent would find a more efficient way of raising its score by instantly spawning in resources, which is not allowed explicitly. And then it can teleport them directly into the machines. And then it got millions of production score after that, which is an invalid part of the score. But I think it's worth noting that you have to still be very careful with your evaluations with cheating. Harnesses that reflect are actually even better at cheating because they're able to score maximize the scalar number by any means. And so you have to be very careful with that. All right, so this is my final slide. Thank you guys so much. I think we have some time to take a couple questions. Today, I presented some work on Continual Harness, which is our archive paper on Pokemon, as well as ArcAGI3 with Gemini 3.1. And then finally, I showed some extensions to a general coding agent called Opus 5. Yeah. I see a hand raised from Seaway.
Yes. Thanks for your talk. It's very insightful. And before anyone asks a question, I do have some questions for you. So wait. So what exactly convinced you that the harness, not just a stronger base model, is where the real leverage is?
Yeah, so I think that what happens is that you have these models that are really good at coding, math, and science. And they should be good at like the symbolic reasoning about like being able to think through and structure these problems. But if you think about a problem, I started as big into reinforcement learning. If you think about a problem, you have the agent and the environment. And there's this loop where the agent receives an observation from the environment and then leverages that to produce some action. And then you can think of some reward that might, or some feedback or verifier that would go back to the agent in order to leverage it forward. And this is kind of a paradigm that you want the model to do intrinsically. but a lot of these models, they don't have the reasoning capacity in order to um, do this structure. And so the idea is to create the most general abstractions such that it's able to stay on task across long context. One of the reasons why we look at harnesses to begin with were context. If you remember, the earliest harness was just running compaction, where we're just asking the model to compact its history so that it can figure out what to do next. In addition to having this compaction, we have things like memory now or subagents, and all of these are revolved around efficiently using tokens and memory, explicit like memory outside of the model. And so I think that the most interesting part of a model with respect to the harness is that you could kind of think of the model as like a Turing machine. But modern computers are not just a Turing machine, they're von Neumann. They have a memory that they can read and write to. And so it's important to think about that with respect to models. The model itself is the Turing machine. It has the tape that continues to execute instructions across. And the von Neumann computer is the harness plus the model.
Okay,
Next question.
thanks. Yeah, and another question is, when an agent learns from its past attempts, so the trajectory, how do you keep it from quietly reinforce some old mistakes, especially in domains where you don't have clear test signals like you do in the coding? I believe this is a question lots of people doing research on self-evolving and continual harness want to ask.
Yeah, so it's definitely like the way I see the paradigm is like first develop a model. It has lots of great innate
I think you are mute or somehow I can't.
how about now? Can you hear me all right?
Just connection issue. I can hear you.
Here, I'll
hear
just stop
Yeah.
sharing. Let's see if that helps. So the question was,
I can't hear you.
I think it's your network issue, Sui.
let's just give this a minute. Oh, I guess he left. Let's give it a minute to join back.
I actually got a question, Scythe. Yeah.
Yeah.
So in your experiments, was the same model used for both like agent and refiner?
Yes. Yeah, we use the same model for all like any
Yeah.
subagents, but also the same model.
And from your experiments, is there any particular model that was being most effective for the refiner? I think you have tried different models for different tasks, but just for the particular role for refiner, is there any like do you have any?
I think it kind of follows. We haven't done ablations for that particular problem. We used we just assume that we're trying to evaluate the model across all of its capabilities at once. But I think that's very interesting. I think that especially when you care about token costs or speed at which you're doing these operations, potentially you might want to have a smaller model that goes over the information, processes the trajectory if you have a very long trajectory, and then you would still have a very strong model. Like you want to use a frontier model, like maybe like Kimi K3, right? And then that model would be making the decisions and the edits at the end after the processing. It's hard to say. I don't have evals in front of me about this, but I think it's a very interesting research direction to figure out what models to use for what, and very, very practical. A very naive way is just use the best model, but like I said, it's very naive.
Thank you. So I think the effort of design this refiner is also like quite. I don't know how much effort have you used to design the refiner. How many trying to get this like performance?
Yeah, I think this is very difficult because we don't want to, we are kind of doing like meta harness optimization as the human in the loop who's creating the refiner. And so we have to give it some prompt about like what to do. And you can imagine that eventually the models could also update its own refinement prompt, right? And then this abstraction can build on itself. We could have like a meta refiner. This is, in my opinion, quite like a nerd snipe. Like it sounds like it's very good, but we need to work on the harness at the frontier of what models are able to do, so that the next generation of models can have these like very natural reasoning traces in order to do the same capability. And right now, the edge case is like how to get the model to use refinements properly, right? We actually want the skills, memory, subagents to be good. And so right now it's okay to edit the prompt very heavily for refinement. You can kind of think of refinement as like a compaction prompt, right? People are still writing compaction prompts ourselves. We're not asking the model to write a compaction prompt and then go compact. It's a skill that we call, and we have a very human engineered performance about this. I think that there's a lot of papers to say whether like skills are better from an agent or a human standpoint. I largely believe that if you have someone who's spending like hundreds of hours developing a good prompt for these very, very unique skills, it'll still be better than having an agent do it, but not for long, hopefully.
Yeah, just one final question. So for the refiner, do you need to design different refiner for different tasks?
No, we want it to be general. I think that you would get benefits from designing a refiner for your specific task, 100%.
Okay.
But we don't do that because we're looking at this from like a research perspective.
Yeah.
Like if this is a general coding agent harness, we don't want to provide like domain information. But if you're doing like a specific task, go for it.
Agree. Yeah. Thank you very much.
Are there any other questions? Don't be shy.
I think there is a question in the chat. Maybe someone couldn't, not convenient to. Can you read it?
Yes, I can read the question from Wilfred. Thank you for the great talk. I wonder if the details of the gyms in Elite Four are exposed to the agent so they can measure how good its team now. Would the agent trajectory be like skipping some events and just go directly to get the Elite Four as long as the team is good enough? This is a really interesting question because like when we were doing the Elite Four runs, like we were running from the beginning of the game. And so the decisions like at the end are heavily influenced from earlier decisions along the way. If you are worried about like data leakage, I definitely think that like the Pokemon games are heavily leaked into the models. So if you ask the model directly, make a set of objectives for every step of the game, including what Pokemon to catch on which routes, it can give you a very explicit guide with respect to this. And so it can do that. But if you don't ask it to do that up front, it is actually very bad at going through the objectives, and it has a tough time figuring out what decision to make next. I think of this as the ability that the models they're very good at long-term planning if you explicitly are doing upfront long-term planning. But if you ask it to kind of like figure out in the long term what to do from a short horizon, they're very bad at that. And honestly, that is a harness level decision. There's like in Codex or Cloud Code, there's /plan. So you can make a plan first and then execute it. I think that's very important. Okay, next question. Are there any specific use cases of Prime Agent that you found interesting in your personal experience when compared to other coding harnesses? Yeah, so I think that one of the interesting things about Prime Agent is that it's able to leverage sub-agents very smoothly. It's the best experience I've seen. It's able, and they're able to not only message each other, but they can they will automatically collaborate over shared resources, and it's very smooth in their operation. And that's like my favorite thing. I used to work on multi-agent communication, so I love that they're able to do that so well now. How does the model refiner update outdated memories, and how does it manage an ever-expanding skill set? The model refiner has basically, you can think of it as like a skill MD that it has the list to, and we tell it to update with respect to experience. So we say, look at the experience, look at how well it's doing, and then make the updates. We give it a very generalized prompt for this. How does it do it? It does it very poorly. As I've shown, a lot of the skills that are created are useless. It's not, if you know coding agents, they create lots of code, but they don't really delete a lot of code. So there's lots of slop code that's created. And in the same way, we have lots of unnecessary skills that are not being updated or deleted properly. And so I think that, but this is largely not a harness issue. The abstractions are correct, but the models are not able to leverage the abstractions efficiently, which is why I say like the next level of models will be trained on this type of harness in order to leverage those extractions correctly, and where we should see a lot better performance about maintaining and creating skills. Wilford, glad that I answered your question. Yeah, Pokemon is definitely in the training data by now. Kirun, thank you for your insightful talk. As the agent evolves, its behavior and failure distribution also change. Since the refiner is not independently optimized, can it remain reliable for continual harness updates? That's a very good point. Right, we see different failure distribution. We see different types of skills that are necessary. If I remember talking about like the topology of the thinking traces from Gemini Plays Pokemon, where some would think very broadly, while others would think very deep in terms of like a tree. But I would like to think about this in terms of like when we ask like how does refine work? Similarly, we should compare it to how does compact work? Because I imagine there are two types of very similar updates where they're explicit reflections on your trajectory for some optimized outcome. For compaction, it's to have important information in context. And for refine, believe it or not, it's actually it's still to have important information in context, but it's to look at the external context rather than the internal context. And so when I look at refine, I think of it as a general prompt. I don't want it to be for a particular task that we're looking at, but I think it'd be very interesting to see if it could, and I think it would do better. Like if you're doing like an auto research task, being able to update the refine specifically for auto research and have like guidance about what to do. I think that is a really like interesting way to do it. And if you have a very like domain specific problem, I would think that that's very useful and correct. We have a Jin Yuan. We have a raised hand, so we'll go to you next.
Can you hear me?
Yes.
Yeah. Okay. Thank you for the great talk and very exciting results. Actually, I have some questions regarding the mechanism. So, in your approach, there are 4 components that are being updated, right? Prompts, memory skills, and I think the refiner use quite general markdown skills to update those components. Then, specific mechanisms the whole system use to decide what kind of actions the agent should or the LM should take to update a specific component, like how the system should decide, like currently I should update skills or update memory, and are there any evaluations involved?
Yeah, so I think that part of our paper was like we saw lots of people, doing prompt optimization for these types of things, but they weren't evaluating them. So, you want to have some sort of verifier that you can compare against in order to understand if these are good. Refining is kind of like using LLM as judge. We're directly asking the LLM to score what's going on and then make the updates with respect to it, as well as search over the information to find what is interesting about the trajectory over time. This what I'm naming is like 3 different components, and I think you need all of them in order to make the system work. But each of them individually, we could definitely have more evaluation into each of them. I think that you could write an entire paper just on like memory, for instance, just reading and writing from external memory. And so I think that like if you wanted to, like same thing with skills, as skills, memory, compaction, all of these you could write an entire paper on. We're trying to make systems that work and measure a balance between making systems that work and are useful for specific hard tasks, as well as have enough evaluations to know like what we're doing is actually helping. I think as a researcher, it's a very difficult problem in order to balance between the two. My approach is to be very application oriented. So we're developing the system because we want to get better at, let's say, playing Pokemon. Another way would be saying, okay, let's just look at the refine. let's figure out the best way of doing refine. There's papers that look at that, like there's JEPA. JEPA is a great paper, GEPA, and that looks at it's not a reset-free domain, but it looks at like how do you do prompt optimization correctly for that exact reason.
Okay, thank you.
Since I think we're getting to the end of the meeting, but there are still two more questions in the chat. Maybe let's answer those 2 questions, then we close this meeting, right?
Sounds great. Let
Okay.
me go through the 2 questions very quickly so we get you guys out of here. Okay, so the paper shows benefits of continual harness learning on the underlying capability of the model. Flash, high variance, flashlight, worse, yes. Are there any metrics that you would have used before committing to a long run to determine whether a model has reached the capability threshold to benefit from continual harness? Yeah, so let's say a new model comes out tomorrow. You want to say, can I use, like, let's say GPT 5.6 came out, right? Do I use Sol, Terra, or Luna? And this is very much not just like what model you can use, but what's your budget. So there's a certain cost to running it for like a certain amount of time, and then what performance you're looking to get. It can, depending on if this is a capability that you can solve, like for Pokemon, only the best models are actually able to solve the game. And it may be actually more expensive from a smaller model to reach the same performance. And so the cost per token of the larger models might actually be lower after the full trajectory comes out. If I were to do an evaluation, I would do exactly what we did. Instead of running the entire game, we looked at the first gym, and then we looked at going to the third gym. You can leverage, even in long horizon, you can leverage smaller portions and try to extrapolate behavior from there. And that's what I would recommend doing, is try to look at what is the minimal amount of time you need to, or like number of tokens you need to run in order to test it out. And then you can scale up behavior afterwards. Okay, last question. How do you think we should design feedback that is low noise and reliable? That is a really interesting question. So feedback, you mean like verification feedback, and it depends on different run. The reason why a lot of the prior model families were not able to work with this is exactly that. They aren't able to do good feedback. The judging capabilities are the most strong capability that limit performance for something like this. And so I would like the best model, I think, are the best models that are really good verifiers. How do we design good verifiers? There's a whole set of tricks. I don't know if I have enough time to talk here, but let's say for Pokemon, you could test out, is the verifier working correctly? And you could do a test with some human labels to figure out how much noise and how reliable it is from there. Afterwards, I would say very traditional training, things like GRPO in these type of domains could probably work like really well to extrapolate. A lot of the domains that we test in are like we think about as out of distribution. And so for any like economically viable task, you would get those in distribution and then do a train and test set. All right.
Okay.
I think that's it. I also thank Tesu, who's been who's one of my co-authors who's in chat today. He's answering some of the questions. So appreciate you for coming, Tesu. Let's end there then, Sue.
Yes.
Oh,
Thanks
just
a
want
lot.
to say thank you, Seth. Yeah,
Yeah.
Nice.
Thanks
thank
a
you for your
lot.
time. Thank you, and bye, guys.
See you. Bye.
Thanks, everyone.
Thank you. Bye.